Wow! Astronomers just discovered that the solar system is moving way faster than it should. One trusted cosmic speedometer says we're cruising at a normal pace. But a new one says we're racing through space at a speed that should not even be possible if our physics are right. So it seems that either something out there is pulling us, or one of our basic ideas about the universe is seriously wrong. Now, when we move, things in front of us react more than things behind us. For example, if we walk through falling snow, the flakes hit our faces, not the backs of our heads. Ride a bike, and the air pushes harder in front, while the air behind feels calm. The front gets busier, the back gets quieter. That difference alone is enough to tell our brain that we are in motion. In cosmology, this front versus back pattern has a technical name. It's called a kinematic dipole. Astronomers use this principle when they measure how fast our solar system is moving through space. To do this on a cosmic scale, astronomers look at the sky the way we look at the world when we start moving. Only instead of snowflakes or air, they use distant galaxies. These galaxies sit so far away they barely change over billions of years. So they work like tiny markers frozen in place, perfect for spotting the difference between what's in front and what's behind. If the universe is smooth on the biggest scales, you'd expect the number of galaxies in each direction to be about the same. It doesn't really matter where the Milky Way is pointing or how we're spinning. The sky should balance out. But if our solar system is moving, one side might seem a bit more crowded because we're flying into it. It's the same trick as noticing more rain hitting the front of your jacket when you run forward. So, astronomers created huge maps of the sky using radio telescopes, which are good at picking up galaxies that shine in radio waves. Radio waves travel through dust, so the view stays clean. They counted how many radio galaxies appear in every direction to see if one side of the sky really is busier than the rest. And that's when they noticed something strange. The side of the sky we're moving toward was much more crowded than expected, like someone stuffed extra galaxies into that patch. This could mean we're moving faster than the standard model allows, or the galaxies are unevenly spread. We already know our motion from another source, the cosmic microwave background. It's the leftover glow from the Big Bang, and it works like a giant universal speedometer. For decades, it's given us a stable measurement of how fast the universe is moving. But this new result does not match that value at all. That extra crowding in the sky isn't supposed to exist at that level. Our best model of the universe says that when we zoom out far enough, the cosmos should look smooth and even. This result makes scientists scratch their heads. The pattern in the radio galaxy map was much stronger and more lopsided than expected. It lined up almost perfectly with the direction we're already moving, as if something out there was pulling harder than anything we've put into our models. Now, scientists just didn't look at one map and call it a day. They checked the result using several sky surveys made with different kinds of radio telescopes. One of those was LOFAR, a giant web of antennas spread across Europe that listens to the lowest, faintest radio signals, combined with two other large radio surveys. It's like taking 3 pictures of the same scene using 3 totally different cameras. If one of them added a strange color or distortion, the other 2 would catch it. But here, all 3 showed the same odd result. The dipole they measured is about 3.7 times stronger than what the standard model of the universe predicts. That's not a small calibration problem. That's a "your calculator must be broken" kind of difference. To understand how impossible this is, imagine checking 2 speedometers at the same time. One of them is the reliable one we always trust. That's the cosmic microwave background in this situation. It says we're moving at a normal speed. But the second speedometer suddenly claims we're going more than 3 times faster, like 200 miles per hour inside a parking lot. We would know something was off. Both readings can't be right. This is the problem. The CMB gives a solid decades-old speed, but the new radio galaxy result is showing something different. 2 measures that should match are telling very different stories. So what could be the reason for these broken calculations? Well, one idea is that the universe is not as smooth or even on large scales as our model assumes. We expect that if we zoom out far enough, everything should start looking roughly the same. But this result hints that the large-scale universe might be more uneven than that. Maybe some huge regions are a bit richer in galaxies, while others are emptier, and those differences add up across the sky, creating a dipole stronger than the standard model predicts. If that is the case, the extra radio galaxies are not a mistake. They are a sign that the cosmos does not follow the straightforward pattern our model assumes. Now, another idea is that something genuinely huge and nearby might be pulling on our whole region of space. No, sadly, not some giant space monster messing with our system from another dimension. The universe already has giant walls of galaxies, long chains of superclusters, huge clumps of dark matter, and massive empty voids that stretch for hundreds of millions of light-years. These things are so large that they can change how entire regions of space move. It's not a sudden yank, more like a slow, constant tug on everything nearby over a very long time. If there's something like that close enough, we can't see it. A wide stretch of space is hidden behind the Milky Way's own dust and bright stars. Astronomers call this the zone of avoidance because our telescopes can barely look at what sits behind that glowing band. We already know there's a large concentration of mass in that blocked region called the Great Attractor, which was my nickname in high school. And some researchers think something even larger could be sitting deeper in the same direction. Now, if that's true, then the strange pattern we see in radio galaxies might not be a mistake. It could be the first hint that something huge is tugging on our whole galaxy region, and we simply haven't mapped that part of space yet. Finally, the third idea is that something is off with the model we use to describe how the universe works. A model is just a big set of rules, like a recipe. Our current one explains dark matter, dark energy, how galaxies spread out, and how the cosmos changes over time, and it expects the universe to behave in a smooth, predictable way on huge scales. The radio galaxy result does not fit that picture. It behaves like a number that refuses to match the rest of the equation, so scientists have to take it seriously. It could mean that matter and energy spread across space in a way we did not build into the model. That would not break physics. It would just mean the rules need an update. So, what happens next? A bunch of powerful new surveys are coming online, and even though they weren't built specifically to solve the dipole problem, they're going to be extremely useful for checking it. The Square Kilometer Array and the Rubin Observatory are all going to map galaxies in way more detail than the older surveys we use now. With cleaner, deeper data, these instruments may help us determine whether the strong dipole is real or fades away when we look at it with better tools. None of these are special missions made just for this question, but the next round of observations will test it naturally. If this strange motion turns out to be real, then something big is shaping our whole region of space. If it's not, then we just learned something important about how easy it is to fool ourselves with patterns in the sky. Either way, we get one step closer to understanding the universe and its puzzles. Our universe is starting to glitch, and it looks like we're going through the biggest tension in astronomy since Einstein redefined gravity. But scientists aren't having a cow yet, because this kind of chaos usually means we're about to discover something huge. So let's run through the biggest issues driving the crisis. For decades, cosmology ran on the idea that the universe should look uniform in all directions for anyone anywhere within it. They call this idea the basic cosmological principle, not to be confused with the cosmetological principle, which states all women should wear a color of lipstick right for them. But I digress. Cosmologically speaking, it means you might see clumps up close, but on massive scales, everything should smooth out. Because of that, scientists figure no structure should be bigger than about 1.2 billion light-years. Yeah, that's big. So they were more surprised to find a structure called the Big Ring. This thing is nearly a perfect circle made of galaxies and galaxy clusters, and it's about 1.3 billion light-years wide. Now, a light year is the distance light travels in a year, and since light is the fastest thing in the universe, that already tells you how enormous this distance is. If your eyes could see it, it would stretch across the sky like 15 full moons lined up side by side, see? And the Big Ring isn't alone. A couple of years earlier, the same astronomer spotted something called the Giant Arc, a curved structure stretching 3.3 billion light-years. Then there's the giant GRB ring, found in 2015, with a mind-melting diameter of 5.6 billion light-years. The Big Ring and the Giant Arc show up in the same part of the sky at about the same distance from Earth. So there's a real chance they're actually parts of an even bigger structure hiding in plain sight. Now, another scientific drama has to do with something called the Hubble constant. That is, how fast the universe expands, the connection between how far away an object is and how fast it's moving away from us. That number helps scientists figure out the age, size, and future of the universe. The Hubble Space Telescope determined that number with an accuracy of almost 1%. The universe is about 13.8 billion years old. So there was Hubble, and later the James Webb Space Telescope that measured distances to faraway galaxies and figured out how fast they're moving away from us. In everyday terms, they showed that for every million light-years you go out into space, galaxies move away about 45 to 47 miles per second. That expansion speed lines up nicely with a universe that's 13.8 billion years old. But there's another totally different way to measure the universe's expansion, and it looks way further back in time. Scientists study the cosmic microwave background, or CMB, which is the leftover heat from the Big Bang. It's the oldest light in the universe, released when the universe cooled enough for light to travel freely. When scientists use the CMB to calculate how fast the universe should be expanding, they get a slower number, about 42 miles per second per million light-years instead of 45 to 47. Now, that might not sound like much, but in cosmology, that gap is enormous. Both methods are extremely precise, and yet they stubbornly refuse to agree. This disagreement has a name, the Hubble tension. Right now, nobody knows why this is happening. Something might be missing from our understanding of the early universe. Now, just when astronomers thought it couldn't get stranger, the James Webb Space Telescope kicked the door down. It spotted some impossible early galaxies. These galaxies show up just 500 to 800 million years after the Big Bang. According to everything we thought we knew, galaxies at that age should look messy, small, and half-finished. But instead, Webb keeps spotting galaxies that look like they've had billions of years to grow up. They already show organized shapes like disks and bulges, basically the same structures you see in modern galaxies like the Milky Way. Features like that should take several billion years to form, not a few hundred million. It's like meeting a teenager who somehow has the wisdom of an 80-year-old. Now, in some cases, smaller galaxies seem to pack more mass than bigger ones, which also completely flips our expectations. Even cooler, some of those early galaxies contain heavy elements like oxygen and carbon. Stars make those elements, but stars need time to cook them up through nuclear fusion. Seeing heavy elements like that early is like finding baked bread before anyone invented ovens. Either the universe evolved way faster than we thought, or our timeline is missing entire chapters. Another weird headache in cosmology is all about lithium. Yep, the same element in phone batteries. According to the Big Bang idea, the early universe was insanely hot and dense, hot enough to smash particles together and create a tiny amount of lithium. Not much, but enough that we should still see about 5 lithium atoms for every 10 billion hydrogen atoms floating around today. Astronomers can actually check this by looking at stars. They use a trick called spectroscopy, which means splitting starlight into colors to see what elements are inside. Now, to estimate a star's age, they look at iron. Iron only forms in supernova explosions, so stars with very little iron are super old, born when the universe was still young. But here's the problem. those ancient low-iron stars barely have any lithium. Not just a little less, sometimes less than 1/20th of what the Big Bang predicts. And the older the star, the worse the mismatch gets. Scientists call this mess the lithium problem, and it's been haunting cosmology for decades. Some researchers try to explain it by saying stars somehow destroy lithium internally. But every version of that idea crashes into other observations. Instead of getting better, the problem keeps getting worse. And when a simple element refuses to behave, it usually means our picture of the early universe still misses something big. Well, dark matter adds another dark spot to the picture. Scientists invented it to explain why galaxies don't fly apart. It acts like invisible glue. Models predict dark matter should pile up densely in galaxy centers and form sharp spikes. But observations keep showing smooth, soft cores instead. It's like expecting a mountain peak and finding a gently rolling hill. That mismatch shows that dark matter isn't behaving the way scientists assumed at all. Some of them even suggest dark matter might feel a fifth force, something beyond gravity, electromagnetism, and other known forces. That idea sounds wild, but it neatly explains why dark matter spreads differently than predicted. If it turns out to be true, it would change how we perceive the way galaxies form, how they evolve, and how the universe structures itself on every scale. And finally, there's dark energy that has confused scientists ever since they stumbled on it about 25 years ago. It makes up most of the universe, and we still don't know what it is. The default idea said dark energy stays constant, like a built-in pressure of empty space itself. Some theories linked it to quantum fluctuations, which are tiny particles popping in and out of existence in empty space. But when scientists calculated how strong that effect should be, they got a value trillions upon trillions of times too big. So clearly, something didn't add up. Now, a massive project shows that dark energy might not be constant after all. Instead, it might have peaked about 4.5 billion years ago and slowly weakened since then. If that's true, dark energy changes over time. Why does this matter? Because dark energy controls the universe's future. If it stays strong, the universe keeps expanding faster and faster until galaxies drift so far away we can't see them anymore, a scenario called the Big Freeze. If dark energy weakens enough, gravity might slowly fight back, expansion would slow, and galaxies that are currently disappearing could drift back into view. All these problems share something unsettling. They're systematic. They repeat across instruments, methods, and research teams. Random errors don't behave this consistently. The universe keeps giving conflicting answers, no matter how carefully scientists ask the questions. That's why researchers call this a crisis, not because science failed, but because it's working exactly as it should by revealing where our ideas fall short. Now, don't be nervous, but there is a hole in our universe. Is it leaking? It's larger than anything we've seen before. The human mind can't even imagine something this huge. Well, mine sure can't. Is it a growing black hole? Is our solar system going to end up sucked into this giant nothingness? Am I blowing this all out of proportion? Well, let's figure it out. The universe isn't packed evenly with stuff. Huge empty areas, called voids, make up about 80% of it. Our own Milky Way even sits inside of one, known as the local hole. But one void is on a whole different level. It's called the Behoudy's void, and people often nickname it the Great Nothing. It's a massive, almost empty bubble of space located far away in the Behoudy's constellation. Its sheer size makes this bizarre formation unbelievable. The Behoudy's void stretches a whopping 330 million light-years across. For comparison, our little solar system has a width a bit more than 3 light-years. Yet the Behoudy's void contains very few galaxies. Compared to the rest of the universe, it's basically empty. That makes it one of the largest known voids, and one of the biggest empty spaces we've ever found. If our galaxy were inside the Behoudy's void, we wouldn't have seen any other galaxies for most of history. Until the 1960s, our telescopes just weren't powerful enough. Other galaxies would have been way too far away and too faint to spot. It wasn't until the 1960s, when telescopes got much better, that we could finally see very faint, faraway galaxies. If we had been living inside that void, that's when we would have first realized other galaxies even existed at all. But let's figure out a very important question. How do such giant empty spaces even form? After the Big Bang, all the matter in the universe started spreading out, but it didn't spread out perfectly evenly. Tiny random differences, called quantum fluctuations, meant some areas had a little more matter than others. The denser areas had stronger gravity, so they pulled in even more matter. Over time, this left other regions almost empty. That's how galaxies clumped together, and how huge voids were created in between. So over time, galaxies attracted each other too, linking up into long thread-like structures called filaments. Together, those filaments formed a massive foam-like web across the universe. The galaxies gathered along the threads, while the empty spaces in between became voids, kind of like bubbles in foam. Smaller voids slowly merged into bigger ones, which is how enormous regions like the Behoudy's void formed. Today, filaments and voids make up the largest structures in the universe. The filaments are hotter and more energetic, while the voids are colder and much emptier. Now, the Behoudy's void is enormous. It makes up about 0.35% of the diameter of the entire observable universe. But inside this massive space, there are only about 60 galaxies, mostly stretched out in a tube-like shape through the center. Normally, a region this size would contain around 2,000 galaxies. The void is also surrounded by massive galaxy clusters, like Ursa Major, Shapley, Hercules, Corona Borealis, and Behoudy's. This makes the emptiness in the middle even more shocking. Now, scientists first noticed those huge empty spaces and big galaxy groups in the 1970s, when new technology finally let them see the universe in 3D. As for the Behoudy's void, it was discovered in 1981 by American astronomer Robert Kirshner from the University of Michigan, which also has a pretty good football team. At the time, he and his team were mapping the universe in 3D by measuring how fast galaxies were moving away from us. This method is called a redshift survey. So while doing this, they noticed something weird. A huge region of space where almost nothing showed up. It was basically a giant blank spot on the map. Scientists ruled out a few dramatic ideas right away. The Behoudy's void isn't a black hole because it does contain a small number of galaxies, just far fewer than expected. It's also not a dark nebula, which is a dense cloud of gas and dust that blocks out light. The Behoudy's void isn't hiding galaxies. There simply aren't that many to begin with. The Behoudy's void helps scientists learn how the universe changes and grows. Because it's so empty, it's a great place to study dark energy. Our universe consists of normal matter, and dark energy. Normal matter is everything you can see with your own eyes or with the help of instruments. It makes up around 5% of the universe. About 27% of the universe is dark matter, and dark energy takes up around 68%. It's a force responsible for the expansion of the universe. We really don't know what dark energy is, so scientists are excited about any chance to study it and learn more about how it works. Voids are also useful for studying neutrinos, tiny particles that can travel throughout space without getting stuck. They're often called ghost particles because they're almost impossible to catch. They fly through space and through us without leaving a mark. Right now, trillions of them are passing through your body and you don't feel a thing. Neutrinos are made in places with lots of energy, like the sun, exploding stars, and nuclear power plants. They are everywhere, second only to light particles in the universe. What makes neutrinos really strange is that they can change as they travel. They come in 3 types, and they can switch between them while moving. Scientists also don't know how much neutrinos weigh, or which type is the heaviest. Learning more about them could help explain how the universe works. Well, anyway, with time, space missions will look closely at these empty regions. By comparing what they see with computer predictions, scientists hope to learn more about neutrinos and better understand how the universe works. One of such space missions is Euclid. Its data will be used to study and analyze the Bohodi's void and other similar cosmic voids. Euclid's job is to study the dark universe. It does this by making a huge 3D map of space, looking at billions of galaxies as far as 10 billion light-years away and covering a big part of the sky. Now, scientists know that dark energy makes the universe expand faster, and dark matter helps galaxies form and stick together. But they still don't know what either of them really is. By watching how the universe has changed over the last 10 billion years, Euclid helps scientists understand how space grew, how galaxies formed, and what dark energy, dark matter, and gravity might actually be like. Euclid is about 15 feet tall and 12 feet wide. It has two main parts. One part runs the spacecraft, like power, computers, and steering, and the other holds the telescope and two cameras. One takes pictures in visible light, that's what our eyes can see. The other sees in infrared light, which helps scientists spot very distant galaxies. Now, Euclid launched on a SpaceX Falcon 9 rocket from Florida in July 2023 and officially started doing science in February 2024. It now orbits far from Earth, nearly 1 million miles away. It stays in a special spot in space where it moves with Earth around the Sun. This keeps its view stable and makes it easier to study the universe. Euclid is supposed to work for about 6 years, but it might keep going longer if it doesn't run out of fuel. In October 2024, Euclid released the first part of its huge map of the universe. Over time, it'll scan more than 1/3 of the sky outside our Milky Way galaxy, capturing billions of galaxies, some so far away that their light took up to 10 billion years just to reach us. The images taken by the space probe are about 4 times sharper than those taken by telescopes on Earth. Euclid also studies light in detail to learn what galaxies are made of and how they move. It'll do this for hundreds of millions of stars and galaxies. And all of this will create a massive space data library, one of the biggest ever made by a space mission. Oh, by the way, Euclid was named after an ancient Greek mathematician who helped invent geometry, the study of shapes in space. Scientists picked this name because understanding the shape of the universe helps explain how matter and energy are spread through space. So now you know. So, planets with 2 suns, like Tatooine from Star Wars, used to sound like pure fantasy. For decades, scientists believed these systems were too unstable to exist. 2 stars tugging at a planet should fling it into space or drop it into one of the suns. Except, it turns out that nature didn't get the memo. Astronomers have found a planet calmly orbiting 2 stars like it's no big deal. This planet lives closer to its 2 parent stars than any other directly imaged planet in a binary star system astronomers have ever seen. Now, direct imaging means they saw the planet's light, not just its shadow. The whole system sits about 446 light-years away, so the light we see from it today left before humans ever built modern cities. This space monster is roughly 6 times the mass of Jupiter. And even more surprising, the planet is only about 13 million years old. That sounds ancient until you zoom out a little. Earth is about 4.6 billion years old, which makes this planet basically a newborn in cosmic terms. The 2 suns of this monster orbit each other incredibly fast and complete a full loop in just 18 Earth days. That means their gravity constantly shifts, yanking space around them like a cosmic washing machine. Even so, the planet stays locked in its path, so it takes it 300 Earth years to finish a single orbit. So nobody fully understands how this planet formed in the first place. When 2 stars orbit each other this closely, their gravity usually tears apart planet-forming material before anything big can take shape. Scientists have only found a few dozen planets like this so far, and that's nowhere near enough to piece together the full story. To solve the mystery, they need more data. Now, another cool find that still needs more research is a planet so stretched by gravity that it looks like a lemon, not a sphere. This planet is nothing like the calm blue and green worlds we see in space movies. It orbits a pulsar, which is basically a star's corpse. When a massive star expires, it collapses into an ultra-dense object that spins insanely fast and blasts radiation like a cosmic lighthouse. Being near one of those means game over for anything solid. And yet, this planet hangs on, barely. The gravity stretches it, pulling harder on the side facing the pulsar than the far side, like cosmic taffy. And here's where it gets extra unsettling. When scientists analyzed this planet's atmosphere, they didn't find water or oxygen. They found helium and pure carbon. No clouds, no oceans, no chance of life. According to everything we know about planet formation, this world shouldn't exist at all. So it might not be a planet in the normal sense. It could be the exposed core of a star that got shredded, leaving behind something stuck between planet and stellar corpse. That's a pretty scary trend. The line between planets and stars keeps getting blurry. And speaking of scary, meet this guy. This system lives around two red dwarf stars. These two stars orbit each other at a distance similar to how far Jupiter sits from the Sun. Scientists found two Earth-sized planets and a third possible one squeezed right up next to the stars. One planet completes a full year in just over 2 days. Another takes about 3.5 days. The candidate planet orbits even faster. To put that in perspective, these planets sit less than 2 million miles from their star. The Moon sits about 250,000 miles from Earth. So yeah, these worlds are close. When they combined data from space and ground-based telescopes, astronomers realized they were staring at something totally new – planets that transit or pass in front of both stars. Most planets in double-star systems orbit only one star, and this setup shouldn't last long according to the rules of physics. But these planets exist anyway, calmly breaking the rules. So this guy proves that planet formation works in ways we still don't fully understand, and space clearly enjoys messing with our expectations. Now, let's crank up the horror a notch. Astronomers made the first ever 3D map of a planet outside our solar system. And not just any planet. This one is so hot it literally tears water molecules apart. As the planet moved behind its star, the James Webb watched tiny changes in the star's light at different colors or wavelengths. Some colors get absorbed by water vapor, others don't. By stacking all that info together, scientists figured out temperatures at different heights and locations in the planet's atmosphere. And that's how they learned that parts of its atmosphere heat up to nearly 5,000 degrees Fahrenheit, hotter than molten lava. This superhot planet sits about 400 light-years away and weighs around 10 times as much as Jupiter. It races around its star in just 23 hours. 1 year there is basically a day. And because it's so close, the temperatures get so high. Winds try to move heat around, but they totally fail. WASP 18b's atmosphere barely has any water and instead overflows with carbon monoxide. Astronomers once believed water should be common in giant planet atmospheres. This world proves water is optional, not guaranteed. Now, magma worlds are another perfect proof of that. There's a huge group of planets called sub-Neptunes, planets bigger than Earth but smaller than Neptune. For a while, some scientists hoped these worlds were Haitian planets, covered in deep oceans of water or ice, wrapped in thick atmospheres. One famous example was K2-18. Its atmosphere showed methane and carbon dioxide, but almost no ammonia. But as it turned out, lava dissolves ammonia too, so the missing ammonia doesn't prove water at all. It could just mean the planet has a global ocean of magma instead. The researchers modeled how these planets heat up, cool down, and evolve over time. They asked a simple question: do these planets ever cool enough to stop being lava worlds? And the answer was almost never. When they tested thousands of known sub-Neptunes, they say almost all of them are likely lava worlds, not water worlds. In simple terms, these planets don't breathe water vapor, they breathe rock vapor. Their atmospheres come from magma boiling, not oceans evaporating. And that changes everything. Many worlds we once labeled maybe habitable turn into hellscapes the moment you run the numbers honestly. And that means space isn't hiding Earth clones, but mass-producing furnaces and other sorts of monsters. Take this bad boy, for instance. It sits only about 64 light-years away, which is uncomfortably close in cosmic terms, and it's the nearest hot Jupiter to Earth. From afar, it looks stunning, a smooth, deep blue marble floating peacefully in space. But that color hides something absolutely brutal. On this planet, it rains glass, sideways. Winds scream across the atmosphere at around 5,400 miles per hour, fast enough to shred anything instantly. The blue color comes from tiny particles of silicate, the stuff glass is made of, floating in the air. The planet's surface temperature hits about 2,400 degrees Fahrenheit, hot enough to melt rock. That heat turns those silicates into microscopic shards of glass that whip around the planet like a worldwide sandblaster. Standing there wouldn't hurt. You wouldn't exist long enough to ever feel it. And then there's the darkest planet ever found. It reflects less than 1% of the light that hits it. It's darker than coal, darker than black paint. Light just disappears into it. Not all planets even bother with stars at all. Astronomers have found rogue planets, worlds kicked out of their solar systems. These lonely planets drift through space in total darkness, frozen and untethered, with no sunrise ever again. Now, all of this shows us that our universe isn't designed for life. Life survives despite the universe, not because of it. Earth isn't typical, it's lucky. We're only at the beginning of this discovery era. Every year, new telescopes sharpen the picture, and every year, the picture gets stranger. The more clearly we see the universe, the less it resembles our imagination. And that's the most unsettling truth of all. Well, the space object 3I Atlas just whipped past the Sun, and instead of clearing things up, the new images made everything even stranger. Because if this thing really is a comet, then it's the strangest comet ever recorded. And if it's not a comet, then we're watching something completely new invade our solar system. So, should we be worried? This all started back in July 2025. Astronomers using the Atlas Survey Telescope in Chile spotted a faint, super fast-moving object, something unlike anything they'd seen before. That was our first look at 3I Atlas, and right away, scientists had a lot of questions. Where did it come from? What's it made of? But more importantly, what is this thing? At first glance, it almost looks like a tiny cell, right? Like something you'd see under a microscope, with a bright center like a nucleus, and this fuzzy outer layer. But when we look at it from a different angle, the mystery clears up. That glow is actually a comet tail. It's precisely because it looks like and behaves like a comet that NASA finally confirmed it. Yup, 3I Atlas really is a comet. The big giveaway is that it has an icy nucleus and a coma, which is that glowing cloud of gas and dust surrounding it. But this comet is a very special one because it didn't come from our own solar system. It came from somewhere else in the Milky Way, and that's ridiculously rare. To give you an idea, we've only ever seen 3 objects like this, period. The first 2 interstellar visits were the famous Oumuamua and the comet Borisov. And now, 3I Atlas. Cool. But you might be asking, how do we know it actually came from outside our solar system? You see, normal comets are bound to the Sun. They swing around it in these big, looping orbits. But 3I Atlas isn't doing that. Its crazy speed and path show it's not on a closed orbit around the Sun. And the only logical explanation is that it came from another star system and, just wandered into ours by chance. In other words, this is just a visitor passing through our solar system, and is doing it at a ridiculous speed. When we first spotted it, it was going around 137,000 miles per hour. So this object probably spent millions of years cruising through deep space just to hang around our solar system for a few months. And after this quick visit, it'll vanish into interstellar space, and we'll never see it again. Recently, 2 European Space Agency satellites, along with several NASA spacecraft near Mars, captured new images of 3I Atlas zooming in as it passed the red planet. And one of those images is pretty incredible, showing a cloud of hydrogen atoms around the comet. Scientists were pretty excited about that, as every bit of information we get from this visitor matters. Because the reality is, there are still a lot of unanswered questions about this object, starting with its size. We can't pin it down exactly yet, but NASA says it could be anywhere from about 1,400 feet to around 3.5 miles in diameter. Its exact shape is another mystery, because our telescopes can't really get a clear look at it. The nucleus is buried inside this bright coma of gas and dust, and the sunlight reflecting off all that dust basically blinds us. So for now, we're trying to see it through a bright, dusty fog. If you put all the pieces together, its behavior, its chemistry, and the images we've gotten so far, everything points to 3I Atlas being a comet. But even with all that, there are still some pretty controversial ideas floating around about what it might be. Not long after it was discovered, Harvard astrophysicist Avi Loeb said there's maybe a 30 to 40% chance this object isn't something naturally formed. That comment kicked off a wave of online buzz, with people jumping to wild possibilities. Like maybe it's some kind of extraterrestrial tech, or worse, a threat to Earth. Ooh. According to this theory, 3I Atlas might be a massive extraterrestrial mothership. Its odd trajectory could mean it's sending out little satellites toward Jupiter to collect intel for some extraterrestrial civilization. So, in that version of the story, this isn't just a comet. It's basically advanced space spy tech. But then the obvious question is, why spy on Jupiter, right? I mean, wouldn't Earth be way more interesting to an interstellar civilization? Well, in this theory, Jupiter is the target because it's so much bigger than Earth and the other neighboring planets. The idea that a planet that massive could act kind of as an interstellar beacon, something that stands out from far away. The region near Jupiter is another big reason. It's almost like it's an ideal parking spot, where space technology could basically hang out without using much fuel at all. In other words, if you were going to place advanced satellites somewhere to watch a planet, well, that's prime real estate. Pretty cool, huh? But as fun as that theory is, we gotta come back down to Earth for a second. According to the major space agencies, this thing is a comet, case closed. But that label doesn't make it any less special. 3I Atlas is still a total weirdo in the best way, and it stands out for a bunch of reasons. Let's look at 3 of the most important ones. First, this object is old, like really old. Older than me. Scientists think it's been traveling through space for at least 7 billion years. That's so far back in time that it was formed before our Sun and Earth even existed. So yeah, it's probably the most ancient thing we've ever seen in our cosmic neighborhood. Second, its glow. Comets can sometimes look kinda green, and here's why. When a comet gets closer to the Sun, the ice inside it heats up and starts releasing gas. I know the feeling. Some of that gas is made of carbon-based molecules, especially one called diatomic carbon, or C2. When sunlight hits those molecules, they light up, and to us, that glow shows up as green. But with 3I Atlas, that green color is, well, confusing. The data suggests that this comet is actually low on those carbon chain molecules. So, the big mystery is, if it doesn't have much C2, how is it glowing green at all? Well, nobody knows. And now, the third thing that makes this comet stand out. It seems to be giving off a metal alloy we've basically never seen in nature. So this comet is releasing a plume that contains nickel. That's normal. What's strange is what's missing: iron. In comets, nickel and iron usually show up in pretty similar amounts. Here, we're seeing nickel, but no clear sign of iron. And that's almost unheard of. If the data holds up, it points to an alloy called nickel tetracarbonyl, something we've only ever seen before in human-made industrial processes, not out in space. No other known object has shown this kind of signature. Well, now that you're familiar with 3I Atlas, we gotta answer the biggest question of all. Is it a threat to us? Good news! No, the comet isn't dangerous, and it's going to stay really far from Earth. So we can all take a deep breath. Well, I feel better. Although it's harmless, tracking it has been super valuable for planetary defense. You see, space agencies are always watching asteroids and comets, running the numbers on their orbits, and making sure we'd get a warning if something ever did head our way. But 3I Atlas gave them something new to practice with. This is the first time tracking data from spacecraft orbiting another planet were officially submitted to and accepted by the Minor Planet Center. That's the big global database where asteroid and comet observations get collected and checked, so scientists everywhere can stay on the same page. So, in a way, 3I Atlas was like a rehearsal. Gathering data like this from a totally new setup helps researchers sharpen their methods and improve how we spot future space objects. And that means better detection, faster tracking, and more readiness, just in case the next visitor isn't quite so friendly. So get this, Earth might be actually located near space highways that could connect us to other worlds. That's because our sun sits right in the center of a giant bubble filled with hot gas, carved out by ancient supernovae. And this bubble likely has tunnels linking us to distant galaxies. So, does it mean it's time to develop space tourism? Well, let's figure it out. Most of us think space is just planets floating around in eternal darkness. But new research hints at the possibility that it might not be really true. It turns out our whole solar system is actually sitting inside a giant bubble of hot, thin gas. And it gets even better. Scientists now think there might even be a weird cosmic tunnel or channel made of this stuff. It supposedly stretches out toward faraway stars. Astronomers spent years mapping the sky, and after they put all the data together, they found something that looks like a long pathway of hot, low-density plasma, which is basically that very thin, superhot gas. And this so-called channel reaches out from around us to distant constellations. Researchers from Germany confirmed this discovery using data from a space telescope called eRosetta. We'll talk about it a tiny bit later. Now, interestingly, scientists discovered that our solar system sits inside something called the local hot bubble a long time ago. This bubble is actually a huge area, about 1,000 light-years wide. It was created when several stars exploded in giant supernovas millions of years ago. Those explosions heated up the gas around them and basically carved out this bubble of hot, low-density space. And their shock waves created weak points in the bubble around us, eventually forming interstellar tunnels. That cosmic event was so huge that the leftover hot plasma is still floating around us today. Now, to understand this bubble better, scientists used eRosetta, which is an X-ray telescope. It scans the sky looking for soft X-ray light. That's a kind of light we can't see with our eyes. It comes from hot gas, old supernova leftovers, and other structures in space. They also compared eRosetta's new information with older data from another X-ray telescope called ROSAT. And finally, putting all this information together, they were able to make a much clearer map of what's around our solar system. Mind you, this wasn't easy. They had to divide the sky into thousands of tiny pieces and carefully measure faint signals coming from warm gas, empty pockets of dust, and other stuff floating in space. But their effort paid off. After sorting through everything, they managed to figure out the faint glow of hot plasma around us. It proved we were not just drifting through empty space, we're inside a giant burned-out bubble created by extinguished stars. But what really surprised scientists was the discovery of some kind of channel. It looked like a long tunnel in space, cutting through the hot gas around us and connecting our part of the galaxy to star systems far away. They also found signs of another channel pointing toward the Canis Major constellation, and those might not be the only ones. The data suggests there could be a whole network of such paths, branching out through space. Each one works like a hidden back road. Scientists used to guess that the space around our solar system might have little pockets or rooms carved out by old exploding stars. We could probably imagine them like caves inside outer space, but no one had the necessary tools to actually prove it. But now, thanks to that new data from the eROSITA telescope, they finally have a clear picture. The telescope showed that the space around us wasn't just empty. It's full of hot, thin gas and strange shapes, including tunnels and bubbles. This proves at least part of what older scientists predicted. We're living inside a giant bubble of hot gas, and that bubble connects to other bubbles through long, low-density channels. The new study also shows that the pressure inside our bubble is lower than scientists expected. This might mean the bubble isn't closed. It could be open in some directions, letting that hot gas flow out into other parts of space. In short, this hot bubble isn't simple at all. Parts of it might be open pathways, and other parts look blocked off. Being inside it is kind of like trying to walk through a forest. Some areas have clear trails, and others are packed with trees. And even though astronomers have mapped big chunks of the bubble and found these strange channels, there's still a lot they don't fully get. Some paths look like they're made of a bunch of connected empty pockets, and others look totally closed. To understand the whole picture, we'll need better tools and more data. Hopefully, with stronger X-ray telescopes, deeper sky scans, and better computer models, we'll finally understand the nature and structure of the bubble we're living in. We might be able to make a kind of map of those hidden channels and learn how they affect things like cosmic rays, dust, and the solar wind around us. Now, speaking of telescopes, we can't help but mention the one that helped us figure out the very existence of the bubble around us. The thing is, scientists have been trying to understand a faint glow of low-energy X-rays that seem to cover the whole sky. For many years, they weren't sure where this glow was coming from. And then, the NASA-supported DXL mission finally helped to solve the mystery. Researchers used old but reliable detectors that first flew on a rocket in the 1970s. With these instruments, they confirmed that most of this X-ray glow came from a huge area of extremely hot gas around us. It was named the local hot bubble. Back in the 1990s, another X-ray mission called ROSAT made pretty good maps of the sky, and it found something surprising. Comets gave off soft X-rays too. Later, scientists realized this happened when the solar wind, fast particles from the sun, collided with neutral atoms. This process, called charge exchange, can happen almost anywhere in space. Because of this, some scientists started to doubt whether the local hot bubble was really the main source of the X-ray glow. So, to test this, DXL launched on December 12, 2012 from New Mexico. The rocket flew high above Earth's atmosphere for about 5 minutes, giving the instruments a clear view of space. The goal was to look at a worst-case situation where lots of charge exchange might occur. Right now, our solar system is moving through a cloud of cold gas in space, known as the local interstellar cloud. That's also nicknamed the local fluff. Cute, right? Neutral hydrogen and helium atoms from this cloud move through our solar system at very high speeds. Hydrogen gets affected easily by different forces, but helium mostly follows the pull of the sun's gravity. Because of this, the helium forms a focusing cone, a region with extra helium that Earth passes through every December. This cone is the perfect place to look for charge exchange, since it holds more neutral atoms than usual. But what happens during charge exchange? The solar wind comes from the sun's corona, the star's superhot outer layer. The particles in the solar wind have lost many of their electrons. When one of these particles hits a neutral atom, it can steal one of the atom's electrons. The stolen electron briefly gives off a soft X-ray. This is how the glow is created. Now, to compare things, the researchers also looked at old ROSAT data from 1990, taken in a direction away from the helium cone, where charge exchange should be weak. By putting everything together, the scientists found that only about 40% of the soft X-rays come from inside our solar system. The rest, the majority, comes from the local hot bubble. This means the huge cloud of hot gas around us really is the main source of the X-ray glow. But let's get back to the discovery of the space intergalactic tunnel. It's a valuable lesson for us that space might look calm and empty when we look up, but that's not true. Space around us actually contains dust, plasma, radiation, magnetic fields, and mysterious tunnels. All of these things mix and swirl together, making space much more complicated than a simple vacuum. A chunk of rock from a different star system is heading straight toward Earth at a speed 1,000 times faster than a Formula One car. And I'm not talking about some sci-fi movie plot here. Recent research shows that our sweet little Earth could be more exposed to galactic intruders than we believed. These are called interstellar objects, or ISOs for short, and there is a certain part of Earth that has higher odds of getting hit. And we'll get back to it in a minute, but first, let's see what these ISOs are all about. We've only spotted a few so far, like One-Eye Oumuamua back in 2017, Two-Eye Borisov in 2019, and this year, Three-Eye Atlas, the third confirmed interstellar visitor, passed through our solar system. Interstellar objects like Three-Eye Atlas and Oumuamua aren't gravitationally bound to the Sun or any star in our solar system. That's why they're super fast and drift freely through the galaxy until they, by chance, cross our path. But what if one of those does more than just pass by and actually hits us? Scientists ran giant computer simulations with billions of fake interstellar objects flying around, then narrowed them down to the ones that could hit Earth. It turned out that these objects wouldn't hit the planet randomly. Low-latitude zones near the equator are more likely to get smacked. Places just above or below the tropics carry the biggest risk. And before you sigh with relief because you don't live there, there's also a bit more risk for the northern hemisphere, where almost 90% of the human population resides. It's likely to happen in a pattern and not as a random lottery because ISOs are not typical orbiters like asteroids or comets tied to the Sun. They come flying in on hyperbolic trajectories. That's a fancy way of saying they're unbound, just passing through. That means their arrival direction, speed, and relative motion all matter. The simulations show many ISOs are coming roughly from the direction the Sun moves in the galaxy, or along the Milky Way's main disk, called the galactic plane. Looks like the risk of impact also changes from season to season. The fastest potential strikes lean towards spring, when Earth is moving toward the solar apex. But overall, even calmer, slower ISO impacts are slightly more likely to happen in winter, when Earth faces away from that motion. It doesn't mean you should panic. These events are extremely rare, but it changes what we imagined. Astronomical visitor from the stars is no longer just a fantasy, it's a real risk, with a map. And this isn't just theoretical. Earth already gets hit by objects from inside our solar system all the time. Space rocks, comets, asteroids, they cross our orbit. That's why scientists keep an eye on near-Earth objects. Asteroids and comets that come within 30 million miles of Earth's orbit get that title and make it to the NEO list. To track them, scientists use a whole network of telescopes on mountains, in deserts, and even in space. NASA's Pan-STARRS in Hawaii scans the sky every night like a giant radar, takes picture after picture, and compares them. If something moves slightly between the images, that's a potential asteroid. The Catalina Sky Survey in Arizona does the same thing, and it found more than half of all near-Earth asteroids we know today. There's also NEOWISE, a space telescope that can spot dark, cold asteroids that ground-based telescopes might miss. And then there's DART, NASA's first real test of asteroid deflection. In 2022, NASA actually hit an asteroid on purpose to slightly change its orbit. The asteroid wasn't dangerous, but the test worked. And that single mission proved humanity can literally change the path of a space rock if we ever need to. And if all of this wasn't cool enough, NASA is building a new superhero to protect the Earth – NEO Surveyor. It will be the first telescope ever built specifically to detect huge numbers of asteroids and comets that could be dangerous to Earth. Here's why this thing matters so much. The solar system is crowded, messy, and full of objects we can't see with normal telescopes. A lot of asteroids are dark, like charcoal dark, and they barely reflect sunlight. That means regular optical telescopes look right past them. But even the blackest asteroid starts to warm up when the sun hits it, and warm things glow in infrared. That's where NEO Surveyor flexes. Its ultra-sensitive infrared detectors don't care how dark an asteroid is. If it's heated by sunlight, the spacecraft will spot it like a space detective with thermal vision. And the best part is that NEO Surveyor will finally see the asteroids that come at us from the direction of the sun. Ground-based telescopes can't stare at the sun unless they want to go blind. So anything approaching from that direction is basically sneaking up behind Earth wearing cosmic camouflage. NEO Surveyor fixes that. It will also catch the sneaky objects that travel ahead of Earth or behind us in our orbit, the ones that are drowned out by sunlight and slip through the cracks. These are real threats, and bigger telescopes on the ground often miss them. But when they don't miss a new object, they track it for days or weeks to figure out its orbit, basically its path around the sun. They need to know if it's going to cross Earth's orbit, if it will come close, and if so, how close. If it doesn't look harmless, it will go on to the Sentry Risk Table, which is basically Earth's cosmic watch list. So, stuff hits our atmosphere all the time. Tiny meteoroids, something like cosmic crumbs, burn up and give us shooting stars. Sometimes a slightly bigger rock shows off and creates a bright fireball. It happened over northern France a couple of years ago. Astronomers spotted a small asteroid hours before it arrived, and people on the ground got a surprise fireworks show courtesy of outer space. But every now and then, a rock comes in that's not quite big enough to survive the descent, but still large enough to release a terrifying amount of energy when it breaks apart. One example of those was the Chelyabinsk meteor. On February 15, 2013, the locals were just starting their day when the sky suddenly lit up. When it blew up about 14 miles above the ground, it released the energy of 440,000 tons of TNT. Then, a space rock, only the size of a house, slammed into Earth's atmosphere at 11 miles per second. And for a moment, it looked like a sci-fi movie had come to life. The shockwave shattered windows across almost 200 square miles, damaged thousands of buildings, and injured more than 1,600 people, mostly from flying glass. And because it came from the direction of the sun, no telescope ever saw it coming. The crazy part is that it wasn't even close to the kind of destruction a bigger asteroid could do. NASA's planetary defense experts still talk about this meteor like it was both a warning shot and a wake-up call. After this episode, NASA and international partners launched the International Asteroid Warning Network and the Planetary Defense Coordination Office, the folks whose job it is to make sure Earth doesn't get surprise smacked again. NASA is planning rapid response missions to study any asteroid that looks suspicious, and they might even send a spacecraft to check out an asteroid making a super close pass in 2029. Think of it as our planet doing regular health checkups against space hazards. The odds for any person, anywhere, to be hit by an interstellar rock in their lifetime are still minuscule. But what used to seem like science fiction, rocks crossing between stars randomly hitting us, now looks like science fact, or at least science possibility. So the more we understand how asteroids respond to impacts, the better our chances of saving Earth one day. Because you can't protect humans from a dangerous asteroid if you don't know it exists. The equipment that's getting more and more advanced gives us the advantage of time, and in a cosmic emergency, Time is everything.
Did you know that over the past year, around 150 asteroids whizzed closer to Earth than the Moon? But that's not the scary part. It's that some were only noticed after they flew by. And if even one of those had taken a slightly different path, whole cities would be gone. That's what keeps the scientists worried. The invisible stuff hiding where our telescopes can't see. Let's explore what that means. Astronomers keep a list of asteroids that wander into our neighborhood. If a rock's orbit comes close to Earth, it joins a special club we call Near-Earth Objects, or NEOs. That list can include anything from a harmless little space pebble that wouldn't break a window to a rock big enough to cause an earth-shattering kaboom. NEOs are leftover materials from when the planets were forming. Some of that rubble ended up tucked safely in the asteroid belt between Mars and Jupiter, but some pieces got nudged onto paths that cut across Earth's orbit. Those are the ones we care about, because they're still wandering around today, looping around the Sun, and every now and then passing uncomfortably close to us. The biggest objects are the easiest to locate. They are rare and bright enough that they stand out in sky surveys. So far, none of those big ones seem to be heading our way anytime soon. However, the real anxiety comes from the middle class of asteroids. On paper, many of them sit in the potentially hazardous object category, or PHOs, but the nickname City Destroyer explains them better. These rocks aren't huge enough to wipe out the planet, but they could flatten a city and mess with the climate for a few seasons. Some are as wide as a football stadium and hit the atmosphere faster than a speeding projectile. NASA estimates there are around 25,000 near-Earth asteroids at least 460 feet wide, but we've only discovered a fraction of them. Basically, we have solid orbits for less than half of the City Destroyer crowd. The rest only exist as numbers in simulations. We know they should be out there. We just haven't seen them yet. Why are they so hard to spot? Some asteroids are nearly coal black, blending into the cosmic night. Others hang out close to the Sun from our perspective, so our telescopes get overwhelmed by brightness. It's like trying to locate a mosquito while staring directly at the sunlight. Please don't do this. From Earth, these rocks are mostly lost in the Sun's glare. We only catch a glimpse just after sunset or right before sunrise. And that chance only exists if the sky is perfectly clear and the asteroid happens to be in exactly the right spot. If not, it slips back into the Sun's blind spot, playing hide and seek with us. We were caught by surprise quite recently. In 2013, the Chelyabinsk meteor came from the direction of the rising sun. No one saw it in time because it was coming from the wrong direction. It exploded high above the region, shattering windows across the city and sent more than 1,000 people to the hospital. The scariest part is that the meteor was only about 60 feet wide. Now imagine a city destroyer coming from that same direction. A stadium-sized rock stepping out of the sun's glare would give us very little warning, maybe a few days or a week instead of decades. And we know that the blind zone is not empty. Observations have already revealed at least one large asteroid in that region that scientists can seriously consider a planet destroyer. It's called 2022 AP7, and it's huge. This thing is more than half a mile wide, big enough that if it ever hit Earth, it would be a catastrophic day for everyone. Astronomers found it by using the super-sensitive dark energy camera during twilight, pointing the telescope at the region of the sky most surveys normally avoided. The good news is that AP7 isn't headed straight for Earth. Its orbit crosses the orbit of our planet, but the timing doesn't line up, so we won't encounter it this pass, the next one, or even for several centuries. The bad news is what that discovery hints at. If it took this much effort to notice something like this, what else are we missing? And 2022 AP7 is just one PHO. Other asteroids closer to the Sun were also spotted during those same twilight searches. New simulations say some of those hidden rocks are not random. A bunch of them seem to share an orbit with Venus. They do not orbit Venus itself. They orbit the Sun in almost the same lane, sometimes a bit ahead of the planet, sometimes a bit behind, like kids jogging on the same track but spread out along the lap. Astronomers already know about roughly 20 of those Venus co-orbitals, and their paths are anything but stable. Gravity from Venus, Earth, and other planets keep tugging on them, and over thousands of years, those pulls could stretch their paths until they start crossing Earth's orbit. Most flybys are harmless, but one unlucky pass could be the one that counts. So what can we do about this? The first step is simple in theory. Find them earlier. The goal for astronomers is to launch infrared telescopes and get them into space. While we do have amazing telescopes like JWST or the Hubble Space Telescope, they're never pointed at the Sun, as the brightness of our star can damage them. That's why we need a telescope in orbit around Venus, or one that travels along with it. It would be in a much better spot to keep an eye on the asteroids that hang out there. NASA is launching the NEO Surveyor project that aims to solve the problem. It should scan the inner solar system to spot dangerous asteroids in time. Also, we're learning that we can actually move asteroids. NASA's DART mission rammed a small spacecraft into a rock, which affected its orbit slightly. Not by much, just enough to prove that it can be done. It's like turning a plane just 1 degree while it's still across the ocean. By the time it reaches you, that tiny change can make it miss by thousands of miles. Teams around the world spend their days babysitting space rocks, and yes, that's a real paying job. NASA has the Planetary Defense Coordination Office. Europe has the NEO Coordination Center. Observatories feed them nightly sky data, and computers immediately check each dot's orbit. If a rock might wander too close, it joins the risk list and gets extra attention. Each new photo updates the orbit a little more. Sometimes that make the danger level rise for a moment. That is exactly what happened with 2024 YR4, when it briefly reached level 3 on the Torino scale before better measurements calmed everyone down. The scale itself runs from 0 to 10, and anything that climbs above 3 is rare enough to raise eyebrows. The whole system works that way on purpose. Notice something strange, collect more data, then decide whether to relax or stay alert. Most of the job is actually pretty dull. It's a lot of number checking, orbit fixing, and crossing out false alarms. That quiet, careful routine is what lets the world respond quickly when a rock finally appears that isn't just passing by. So how worried should we be? For those huge planet-destroying rocks, the short answer is not much. Nothing that size is on the near-term schedule. Smaller city-level threats are trickier. The odds of one hitting Earth anytime soon are still tiny, but they're not zero. Think of it as a cosmic lottery that has been running for billions of years. Every once in a very long while, the universe draws a number that makes astronomers sit up and pay attention. It's not a reason to panic. It's a reason to build better eyes in space and make sure that if a bad ticket ever comes up, we see it in time to do something about it.
A recent shocking discovery, shocking I tell you, shows that one galaxy can devour another smaller one, leaving behind just faint remains. Can anything like this happen to our home Milky Way galaxy? And if it does, what will happen to the inhabitants of the planet Earth? You know, us. Well, let's figure it out. This whole discovery is actually a curious story. Even before the Rubin Observatory, an astronomical observatory in Chile, even started its full science work, it accidentally helped astronomers spot something totally unexpected. In June, the team released its very first test images, and one of them showed a deep look at the Virgo cluster. That's a huge group of nearby galaxies scientists have been studying for years. But in the bottom right corner of that image, there was something thin and strange, and it wasn't me. It was a tiny razor-sharp streak of stars stretching away from a well-known galaxy called M61. No one had ever seen it before. Now, M61 looks a lot like our own Milky Way galaxy. It's a barred spiral galaxy with long, sweeping arms. But despite the similar shape, the center of M61 is far more dramatic. While Milky Way's supermassive black hole sits quietly, almost as if it's asleep, M61's black hole is wide awake and hungry. It feeds on surrounding matter and blasts out powerful flows of energy, which creates a kind of galactic storm that spreads through the galaxy. M61 has been studied for decades, but Rubin's camera is built to pick up things that are extremely faint. That's why this new star system suddenly appeared. It was as if someone turned on a flashlight in a dark room. Now, the stream is enormous. It's about 50 kiloparsecs long, which is roughly 163,000 light-years. That's more than the size of the entire Milky Way. Most stellar streams around our own galaxy are only a few tens of thousands of light-years long, so this one is huge by comparison. Scientists think that the long trail is made of a dwarf galaxy that got too close to M61. Once it crossed into the larger galaxy's territory, the dwarf galaxy became trapped in its gravitational grip. Little by little, powerful tidal forces began pulling it apart, stretching it into a long, faint trail of stars. Eventually, it was completely ripped apart by M61's gravity. When that happened, the larger galaxy seemed to have responded with a burst of new star-making about 10 million years ago. It almost felt like the collision kicked it awake. This process, large galaxies tearing smaller ones apart, is thought to be one of the main ways galaxies, like the Milky Way and M61, grow over billions of years. Each smaller galaxy that falls in becomes fuel for the larger one, adding stars and gas, and sometimes this process can even stir up activity around the central black hole. Will our Milky Way become that smaller galaxy one day? Well, we do have a much bigger neighbor, the Andromeda Galaxy. But at the moment, we can't predict whether it'll get hungry enough to attack the Milky Way. Whew, what a relief. Anyway, it might seem weird that the M61 stream had gone unnoticed for so long. It wasn't exactly faint or subtle, glowing with the light of about 100 million suns. Hard to miss. But it managed this trick by staying hidden behind a nearby galaxy. This makes it really difficult to detect even bright stellar streams. To find them, we need extremely sensitive instruments and careful techniques. At least now we know that giant galaxies may grow by eating smaller ones, leaving long trails of stars behind as evidence. The researchers admit that it's surprising that such a huge structure stayed hidden around a famous galaxy for so long. And it seems that the discovery of the M61 stream is just the beginning. The night sky might start filling with new, uncovered structures, ghostly trails, forgotten galaxies, and the remains of ancient cosmic encounters. The Rubin Observatory is a brand new astronomy center built on a mountain in Chile. Its full name is the Vera C. Rubin Observatory. It was named after the astronomer who first found strong evidence that dark matter is real. Now, what makes Rubin special is that it's the first telescope of its kind. Its giant mirrors, super-sensitive camera, fast movement, and powerful computers all use cutting-edge technology. The main telescope, called the Simonyi Survey Telescope, has a 27-foot mirror, and it uses the LSST camera, which is the biggest digital camera ever made. But we'll talk about it a bit later. For 10 years, this telescope will take extremely detailed pictures of the southern sky. It will scan the entire sky every few nights, creating a huge, high-quality time-lapse video, the largest movie of the universe ever recorded. This movie will help scientists spot things that change over time, like asteroids, comets, stars that get brighter or dimmer, and exploding stars called supernovae. To create this giant time-lapse, the Rubin Observatory will have to use a lot of new technology. Some of its parts were invented from scratch, and others were improved versions of older designs. It'll help scientists discover all kinds of things. Many we already expect, and many we can't even imagine yet. Even so, Rubin Observatory was built with 4 main science goals in mind: learning more about dark matter and dark energy, creating a complete list of objects in our solar system, mapping the structure of the Milky Way, and studying objects that move or change brightness over time. Everything about the telescope, its huge size, fast scanning speed, and ultra-sensitive camera, was designed to make discoveries in these 4 areas as complete as possible. Rubin's telescope isn't the first telescope with a mirror about 27 feet wide. but it is the first to combine its primary mirror and tertiary mirror into one single surface. Putting both mirrors together is a special innovation that makes the entire telescope more compact. Because of this, it can move faster and get ready for its next observation much more quickly. The telescope's LSST camera is the biggest digital camera ever created. It's about the size of an SUV and weighs around 6,000 pounds. It holds a giant 3200 megapixel CCD array. Just one single picture from Rubin is so large that you'd need about 400 Ultra HD TV screens to display it. It's also the fastest-moving large telescope on Earth. Rubin's telescope can swing into a new position in only 5 seconds and immediately start taking its next image. This speed comes from the telescope's compact design, thanks to its 2-in-1 mirror and its powerful drive motors. They can quickly move and stop the 220-ton telescope mount without shaking it. Even small vibrations can ruin an image, so this stability is a huge achievement. By the way, if the telescope were spinning at full speed, you wouldn't be able to outrun it. Also, Rubin Observatory has a rare combination. It can collect a lot of light and capture a very large area of the sky in a single picture. This means it can spot faint objects spread out over a wide region without needing many separate images. When you add the telescope's incredible speed, you get the perfect setup for creating Rubin's ultra-high-definition 10-year time-lapse of the universe. A fun fact, each Rubin image covers about 10 square degrees of sky. That's the same area as 45 full moons, or about the size of a golf ball held at arm's length. Another cool thing is that Rubin data will be immediately available to scientists in the US and Chile, and to members of Rubin's International In-Kind program. They'll be able to access everything through an online portal, which means that no giant downloads are needed. After 2 years, the entire world will be able to view Rubin data. Rubin will also process new images every night in near real time. If something in the sky moves or changes, the system will send out a public alert within 60 seconds. This will allow scientists to respond quickly and point their telescopes at the event. Each night, Rubin Observatory will create 20 terabytes of data and send out up to 10 million alerts about changes in the sky. By the end of the 10-year survey, Rubin will have produced a whopping 60 petabytes of raw images. It'll be the first time so much astronomical information is shared with so many people.